So in this video, we're just going to review all the different addition reactions that we've gone through so far. But here they're going to be jumbled up. So it'll help to sort of jog your memory, get a sense of what this would look like on a test, or what it would look like in future chapters when you're asked to recall each of these things out of context, just on the fly. Here's this recipe. Do you remember what to do? Okay, so we have an alkene in this first one. That tells you that we're going to be doing an addition reaction. You'd look at the recipe, you'd notice that you have boron and hydrogen, so that should remind you of hydroboration, and then the oxygen in the second step. So this is going to be hydroboration oxidation. We're going to add H and OH. It will be anti-Markovnikov, and it adds syn. So in this video, we're not going to go through the nuts and bolts and go through the explanation for this for each one of these reactions. We've gone through that previously. We're just going to refresh on how to do the synthesis, to predict the synthesis here. So the more substituted carbon is this carbon on the left in the double bond. That's bonded to 3 other carbons, so that is tertiary. The other carbon in the double bond is only bonded to 1 carbon, so it's primary. Because this is anti-Markovnikov, the hydrogen goes to the more substituted carbon, and the OH will go to the other carbon. Now this is syn addition, so both of these would have to add to the same side of a double bond. If one's coming out, the other one would be coming out too. But because neither of those are chiral centers, we don't really have to worry about that. We can erase the hydrogen because it's implied in these skeletal structures, and again, because that is not a chiral center, because this carbon is bonded to 2 hydrogens and therefore is not bonded to 4 different things, we don't have to give the stereochemistry there. And this would be the product, the only product for this hydroboration oxidation. Okay, we go to B. We see an alkene. That means we should be thinking addition reaction as opposed to substitution or elimination. What are we adding? You look at the recipe. You see 2 hydrogens and platinum. So this is going to be hydrogenation. We redraw the skeleton, the carbon skeleton with the sigma bonds, and we're going to add hydrogens. Now the one thing to remember, we're adding 2 hydrogens and we're adding them syn. That's the crucial thing. So one of the hydrogens, if one adds coming out at us, the other is going to have to add coming out at us. They both add to the 2 carbons in the double bond. We just want to make sure this is drawn as proper tetrahedra. Each of those carbons is tetrahedral. So you'd have 2 bonds in the plane, one coming out at you. That means that methyl group needs to be going away. So we redraw it with dashes. Now that's one enantiomer. Because the original molecule, the alkene, was flat, at least this alkene part was flat, the reaction could happen on either side with equal probability. So you'll want to, because we have a chiral center here, you'll want to draw the enantiomer. Now, the enantiomer is if all the bonds switch. So the bonds that were coming out are now going away. The bond that was going away is now coming out. So those are your 2 enantiomers. Notice the hydrogens add syn. And because this is a skeletal formula, you could just erase those hydrogens at the very end. So these are the 2 products you'd get. You'd get them in a 50-50 racemic mixture when you do this hydrogenation. For C, you see an alkene and you should be thinking addition reactions as opposed to substitution or elimination. You look at the recipe to see what you're adding. You see that you have a peroxy acid on top followed by an acid wash. That's the recipe for anti-dihydroxylation. So you can redraw the carbon skeleton just without the pi bond. And where the 2 carbons were that were involved in the pi bond, you'd have 2 hydroxyl groups. One going in one direction, the other going in the other. So if one is coming out at you, the other is going away. Now we do have chiral centers there. Because our original molecule was flat, because this alkene is the carbons in that are trigonoplanar, the molecule is flat, and the reaction could happen equally likely on either side of the double bond. So in that case, you would get the enantiomer, if it happened in the other way. To draw the enantiomer, you just switch the wedges. Solid wedges become dashes, dashed wedges become solids. That swishes the chiral centers, and so these two are enantiomers. The product of this anti-dihydroxylation with a peroxy acid is a 50-50 racemic mixture of those two products. Okay, this next one, we have an alkene. You see the double bond and you should be thinking, okay, addition reactions as opposed to substitution or elimination. What are you adding? You look at the recipe. We see osmium tetroxide followed by sodium bisulfite and water. That's a recipe for a sort of environmentally unfriendly and definitely very unsafe, but also very exquisitely specific and efficient syn dihydroxylation. So we're going to be adding two OHs, and we're going to be adding them syn. So we can draw that carbon skeleton with all the sigma bonds still in place, just without the pi bond, and we're going to add two OHs on each of the carbons that were in the double bond. We're going to add them in this going in the same direction. So either they'll both be coming out, and we just have to watch to make sure that this is tetrahedral. Notice we have two bonds in the plane, one coming out. That methyl group has to be going away. So that's one possibility. We do have chiral centers here, though, and so we have to draw the enantiomer of this molecule because this alkene is flat, the carbons in the double bond are trigonal planar, and so the reaction could happen equally likely on either face of the molecule. So to get the enantiomer, switch all the bonds. If you have a solid wedge, turn it into a dashed wedge. If you have a dashed wedge, turn it into a solid wedge. Again, if you have a solid wedge, turn it into a dashed wedge. And so that switches the chiral configuration, the handedness, of each of the chiral centers. When all of the chiral centers switch configuration, you get the enantiomer. So these two are enantiomers, and you'd have a racemic or 50-50 mixture of those two products. If you do this syn dihydroxylation. Okay, we have an alkene. We see that double bond, and we should be thinking, okay, we're going to be doing addition reactions as opposed to substitution or elimination. Then what are we adding? Well, you'd look at the recipe. You see acid, and really that's aqueous acid. So that is acid-catalyzed hydration. That's the recipe for that. Now, we're going to be adding H and OH. It's going to be Markovnikov, so the H will go to the less substituted carbon. We have to watch out for rearrangement, for carbocation rearrangements. So we'll redraw our molecule just without the pi bond. We're going to use those pi electrons as molecular glue to stick new stuff on that molecule, so that won't stay there as the pi bond. And now we know this is Markovnikov addition. That means the hydrogen goes to the less substituted carbon. The carbon on the left is bonded to 1, 2, 3 carbons, so it's tertiary. The other carbon in the double bond is bonded to 2 carbons, so it is primary. 2 carbons, so it's secondary. So the carbon on the right is the less substituted carbon. That's where the hydrogen is going to go in Markovnikov addition. That means that at first in the mechanism, we're going to form a carbocation on the other carbon in the double bond. Now that's a tertiary carbocation. Next door, you'd either have a secondary carbon. Now, technically, right now, this is a quaternary carbon, but if you do the methyl shift in order to move the carbocation over, it turns into tertiary. So none of those is more stable than where the carbocation already is. The only thing more stable than a tertiary carbocation is an allylic carbocation, and we don't have a double bond in the molecule, so we can't have an allylic carbocation. So it's already in the most stable position it can be in, and so we don't have carbocation rearrangement. The OH will just add to this carbon here. Now we do have a chiral center here. That hydrogen I can erase because it's implied in the skeletal structure. We do have a chiral center here, and so because we had a carbocation intermediate, you'll remember carbocations are trigonal planar for the same reason that the carbons in double bonds are trigonal planar. They're both bonded to 3 atoms and have 0 lone pairs, so they're flat. Well, we saw in SN1 reactions, what happens if a nucleophile attacks a carbocation? You get a racemic mixture. It could attack just as well on the top of that flat carbocation as on the bottom. And so we end up getting 2 products here, one with the OH coming out at us, and another with the OH, the hydroxyl group, going away from us. Now we want to make sure we draw that in a proper way. If it's coming out at us, then we have a bond coming out, 2 in the plane, the 4th one has to be going away. So it'd look like that. And for the other one, if we have 2 bonds in the plane, 1 going away, the 4th one has to be coming out. And so you get a 50-50 racemic mixture of those 2 enantiomers with that acid-catalyzed hydration. In F, you'd see the alkene and you'd think, okay, addition reaction, as opposed to substitution or elimination. What are you adding? You'd look at the recipe, you'd see hydrogen and halogen, so you're going to do hydrohalogenation. That's addition of H and the halogen, in this case bromine, and it's Markovnikov so long as you don't have peroxides, which here we don't, ROOR. So it's Markovnikov addition. So I'm going to redraw that carbon skeleton that you have in the reagents just without the pi bond. Because it's Markovnikov, the hydrogen is going to go to the less substituted carbon. That's the carbon sort of on the right. That's bonded to 2 other carbons, so that's secondary. And there's the other carbon is bonded to 1, 2, 3 carbons, so that is tertiary. So in Markovnikov addition, the hydrogen goes to the less substituted carbon. In the mechanism for this, you form a carbocation on the other atom, so we do have to watch out for carbocation rearrangements. In this reaction. It's on the carbocation is on a tertiary carbon. Next door we have secondary, secondary, secondary. So it's already on the most stable place nearby, so the carbocation here won't rearrange. And the bromide ion will attack and attach where that carbocation was. Here we do not have a chiral center. I can erase the hydrogen because it's implied in the skeletal structure. We don't have a chiral center because going around the ring one direction is the same as going around it in the other. Either way you go, you find the same features at the same distance. So those act as the same type of branch, and so you don't have a chiral center, so you only end up with this one product for this hydrohalogenation. For F, you'd see the alkene, and you'd say, okay, we're doing addition, as opposed to substitution or elimination. To know what you're adding, you would look at the recipe. Now, MCPBA is one of those sort of hidden peroxy acids. It stands for metachloroperoxy, that's the P, benzoic acid. This was one that we discussed when we went over this. So, peroxy acid followed by an acid wash, that's anti-dihydroxylation. So we're going to be adding 2 OHs anti to each other. So we'll redraw that carbon skeleton. We're just going to have where the 2 carbons were in the double bond, we're going to add OHs, and they're going to be pointing in opposite directions. Oops, opposite directions. So if one is coming out at us, the other's going away. One's going away, the other's coming out. Now those are chiral centers, and our original molecule, the alkene, was flat, so the reaction could have just as well happened in the reverse flipped way to give the other enantiomer. So we're going to draw the other enantiomer by switching the stereochemistry of each of those bonds. A bond that's pointing out will now be going away. A bond that was going away will change so that it's coming out. So those are 2 enantiomers, molecules in which all of the chiral centers switch, but otherwise everything is the same. And if you do anti-dihydroxylation with this peroxy acid on this alkene, you'll get a racemic or a 50-50 mixture of those 2 products. All right, in H, we see an alkene, so instantly you're thinking we're going to be doing addition as opposed to substitution or elimination. What are we adding? You look at the recipe. You see hydrogen and boron, so hydroboration, and then we replace the boron with an oxygen. This is going to be hydroboration oxidation. In hydroboration oxidation, you add an H and an OH. It's anti-Markovnikov addition, so the H will go on the more substituted carbon, and they add syn. The H and the OH will be on the same side of the double bond. So we can redraw the structure that we have, just without the pi bond. And those two atoms in the double bond, that's where we're going to add our H and our OH. Now the carbon on the left is bonded to 1, 2, 3 carbons, so that is tertiary. The carbon on the right is bonded to 2 carbons, so that is secondary. Because this is anti-Markovnikov addition, the hydrogen is going to go to the more substituted carbon. That means that the OH goes to the less substituted carbon, and we end up with that product. And we don't have any, technically these would add on the same face. They'd either both be coming out of us or both be going away. But because we don't have any chiral centers, that doesn't matter. We don't have to draw the hydrogen, it's implied in the skeletal structure, and this oxygen could be going either way. Either way it's the same because it's not a chiral center. And so we only end up with that one product for this hydroboration oxidation of this alkene. All right, one last one. We have an alkene. You'd see the alkene and think, this is going to be an addition reaction. What are you adding? Well, you'd look at the recipe. Here we have osmium tetroxide, and they're trying to be environmentally friendly and safe by just using a small catalytic amount of it. That small amount, as it gets used up, will be regenerated by this NMO, that NMO catalyst that we saw earlier. So this is going to be syn dihydroxylation. We're going to be adding 2 OHs, and we're going to be adding them on the same face of the double bond. So we can redraw the carbon skeleton as it is. Actually, let me just make that a little clearer. So redraw the carbon skeleton as it is, just without the pi bond. And where the 2 carbons were in the double bond, we're going to add these 2 OHs pointing in the same direction. So if one is coming out, the other one will also be coming out of this. If one were going away, the other would be going away. Now we want to make sure that these carbons that they're bonded to are represented as tetrahedral, so we'll have 2 bonds in the plane, one coming out at us, and the other one needs to be going away. So the methyl group there is going to be going away. Again, on the other one, 2 bonds in the plane, one coming out, the other one should be going away. So that's one of our products. We do have chiral centers though, and so we have to draw the enantiomer, because the original molecule, the alkene, was flat. The carbons in that double bond are trigonal planar, and that means the reaction can happen with equal likelihood on either side, either face of the double bond. So to get if the reaction happened on the opposite face, you'd get the enantiomer. All of the solid wedges turn into dashed wedges. All the dashed wedges turn into solid wedges. So again, all of the solid wedges turn into dashed wedges. All of the dashed wedges turn into solid wedges. And so that is your second enantiomer. If you did this syn dihydroxylation with this alkene, you would end up with a racemic or 50-50 mixture of those 2 enantiomers. So hopefully this video gave you a sense of what it's like to think of these reactions out of context, not in the middle of a discussion where it's always the same reaction repeating all over again, but in a series of reactions where you could be doing anything, and you just need to recall the recipes and how they affect molecules, just because you know them so well.